Hey everyone, so we just finished talking about free falling motion and pretty much the idea of objects falling in air. We're going to take that a little bit further where we're going to actually look at the conceptually what ends up happening in non-ideal cases where there exists air friction. All right. Now, we're going to talk a little bit about air friction. So far, all these questions that we've talked about have been ignoring air friction, the ideal cases. Well, what happens when we actually do have air friction? Now, the good thing is the AP doesn't actually want you doing any calculations with air friction, or at least no tough ones, because air friction requires an understanding of calculus and being able to create differential equations. This is algebra based, so all you need to know about air friction is the conceptual thing. What causes it? What are the factors of it? And generally, what are some unique things that come about of it? Well, as you may know, air friction comes from the fact that when objects are moving through the air, the air particles, basically interact with the material. They bump into the material and cause it to experience a drag force. This drag force causes the velocity of the object to start decreasing a bit, essentially adding in an additional acceleration in the other direction. So normally we have objects falling to the ground at with an acceleration of negative 10 meters per second squared. This will have an air friction will end up causing a little bit of an acceleration going upwards that will be, let's say, 2 meters per second squared. That changes the overall acceleration. So this is actually the reason why when we drop objects in the real world, like we drop a feather in a penny or a piece of paper in a textbook, why they don't look like they fall at the same rate. Technically, they should. And in reality, they would if they were only affected by the acceleration of gravity. But due to the fact of air being prominent in our atmosphere, um, the different shapes of the objects, the masses of the objects, just the general uh, differences in the objects themselves will end up resulting in them hitting grounds at different rates. And that's because of this air friction changing the acceleration and decreasing it. Now, a few things to note is first, the air friction always ends up acting in the opposite direction it moves. So if the object's moving downwards, air friction's up. It's thrown upwards, air friction's going down. It goes off on the side, it goes in the other direction. The other thing to note is that speed actually plays a part in this, as we'll mention later on. So, some of the different things that affect the air friction that an object experiences. Well, one of them is the density of the fluid or the air. For example, if you go to Mars that has a much thinner atmosphere, or even go into higher up in our atmosphere where the air is a lot thinner, you'll experience a lot less air friction than if you went to somewhere like Jupiter or even in the water. Even though the water has a bunch of other things going on with it, there is also that quote air friction affecting objects as it moves, basically keeping it from moving as fast as it would. The shape of the object also plays a factor. So this is one reason why if you actually take a piece of paper and you keep it flat and you drop it like that, it'll kind of lilt down to the ground. Uh, but if you roll it up into a ball, you'll actually find that it does fall at a fairly normal rate compared to a pencil, a baseball, a textbook. So the shape also affects it. The more aerodynamic it is, the more spherical it is and smoother it is, it's going to fall with a lot less air friction. In fact, there is a one of the ways that pitchers tend to throw very unique pitches, curveballs and sliders and all that, is actually due to the fact of the orientation of the stitching in the ball and causing one side being affected by air friction more than the other. So all this stuff actually does play a part in this. And then there's also this relative velocity. This actually means that the faster the object travels in the air, the more the air friction actually affects it. So, as the object's thrown to the ground, what's going on with the air friction uh, as the object falls? Well, it actually increases. So, as it falls and it starts picking up speed, the faster it travels, the more the air friction acts on it until it reaches a point where it kind of ends up balancing out with gravity. So gravity is always accelerating the object downwards at a constant rate, but the air friction is going to be accelerating upwards increasingly until this point where eventually the acceleration drops to zero. So once it drops to zero, it can't get any faster. So there's no way for the air friction to start, you know, becoming net upwards essentially. Because of the fact that eventually the acceleration will end up reaching zero, that means that the object will stop speeding up and it reaches this point that we call terminal velocity. Terminal velocity is essentially the fastest speed that the object can travel due to air friction. And once again, kind of going back to the factors that affect air friction, this terminal velocity is dependent on things like the mass of the object, the shape of the object, the density of the fluid, all this stuff. So going back, I said before that, you drop a penny and you drop a tennis ball and you drop a feather, and they all hit at different rates. A lot of that comes from the fact that not only is the air friction changing their net acceleration, their average acceleration through the fall, but they also experience different terminal velocities. The feather basically reaches its terminal velocity almost immediately. The penny, similarly, will reach its terminal velocity a little bit later than the feather, but much sooner than the tennis ball, which is why it kind of lands a little bit later. And if you increase the height or the distance that they're allowed to fall, it becomes a lot more noticeable once it hits that terminal velocity. And then the tennis ball, because of its shape, because of its mass, will have a higher terminal velocity than the others. The reason why this is actually important is because when you do labs, you kind of want to keep track of this. That if you have objects that are falling in the air, you want to make sure that you're choosing objects that won't be affected by air friction, or at least minimize the effect of air friction. So choosing a light ping pong ball for a falling setup, for a falling experiment, is not as good as choosing a very dense metal ball bearing because of the terminal velocity and the air friction effects. All right, so here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so my first recommendation when doing this is to draw the ideal case. Draw what it would look like without the air friction. For velocity and acceleration, it will look like this, as we already found. Once we have the ideal path, what we can then do is, well, first off, with air friction, initially the velocity and the acceleration will start following the original path. So the velocity will initially follow along this dotted line, and the acceleration will also follow along that dotted line. Now, as far as what the graph will end up looking like in the long term, we have to think about what the final end goal is for velocity and acceleration. For velocity, it will eventually reach terminal speed, a point where the velocity remains constant. So eventually, at some point, the velocity will reach a constant value. So I could just use my graph and connect the initial path that goes with the line to the constant graph. And I end up getting a graph that looks like this. Same thing for acceleration. I know eventually the acceleration is going to decrease until it reaches zero. So that's the end goal. Once again, I start with the original path, then I connect a line going to the end goal of zero acceleration, and I end up getting this pattern. And that's pretty much all you really need to be able to do for these the air friction stuff. Like I said, you mainly need to understand what factors affect it, the fact that it results in terminal velocity, and what the graphs will end up looking like. Some quick notes about terminal velocity. So, the Empire State Building is just tall enough so that humans will end up reaching terminal velocity by the time they hit the ground. That basically means that a person jumping from the Empire State Building or uh, all the way up in from a plane above will end up hitting the ground with the exact same speed. Uh, you know, good thing to note. The other thing is this. Now, that terminal velocity is significantly lower than the speed of sound. So people who free fall at no point break the sound barrier, except Felix Baumgartner was the first and only person to actually break the sound barrier during a free fall. Uh, and he did this by changing his terminal velocity so that he actually went faster than the speed of sound. Now, a good question is, how did he do this? Well, when he fell from a point really high up in the atmosphere where the air was significantly thinner. So for him, his terminal velocity was much higher than the normal humans down, near the surface of the earth. So that right there allowed him to not be affected by air friction as much and accelerate for a longer period of time to a much higher final speed. Now, another interesting thing to note is that the way he actually ended up breaking the sound barrier was by also jumping from that height. Not only was his terminal velocity much higher because of the lack of air friction, but it turns out that the speed of sound was actually much lower as well. So he kind of ended up uh, breaking it due to both factors at once. So just an interesting thing about terminal velocity. That's pretty much it for this. We'll continue on where we talk about throwing the object up in the air. Like I said, the main thing that you want to take away from the whole air friction stuff is, what causes it, what are the factors that affect it, and conceptually what the graph should look like. All right, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.